Diffie-Hellman key exchange, also called exponential key exchange, is a method of digital encryption that uses numbers raised to specific powers to produce decryption keys on the basis of components that are never directly transmitted, making the task of a would-be codebreaker mathematically overwhelming. The Diffie-Hellman key exchange is a method of securely exchanging cryptographic keys over a public channel, and was one of the first public key protocols as originally conceptualized by Ralph Merkle and named after Whitfield Diffie and Martin Hellman. Diffie-Hellman is one of the earliest practical examples of public key exchange implemented within the field of cryptography. We will definitely look at the math behind the Diffie-Hellman key exchange, but before we do that, I'd like to share a very simplified analogy using colors, which may help those students that are better visual learners. The concept of Diffie-Hellman is much easier to understand with this color analogy. Let's say that Alice and Bob would like to agree on a common shared secret color that they don't want any other person to know. Here's how they might do this. First, Alice sends a message to Bob telling him a common color they might use. Let's say that Alice selects green and tells Bob the color by email. Next, Alice and Bob each select a secret color of paint that they don't tell each other. Alice's secret color is red, and Bob's secret color is blue. Alice and Bob then each take the common green color and mix it with their secret color. For Alice, green and red make yellow, and for Bob, green and blue make cyan. Alice then sends a message to Bob and tells him that she got yellow as her result. And Bob tells Alice that he got cyan for his result. Alice and Bob now have two colors created by mixing the shared green color with their partner's secret color. They then mix their own secret color with their partner's shared color. For Alice, she mixes cyan and red to get teal. For Bob, he mixes yellow and blue to get teal. Both of these teals are identical and were created by mixing together the same three colors: green, red, and blue. Now let's assume that a malicious person is watching all of the messages that Alice and Bob exchanged. What would he know? Well, he knows that they started with the color green, and he knows that they exchanged the colors cyan and yellow. He would not know either of the two secret colors that Alice and Bob selected, which are red and blue, or the common secret color of teal, because those were never sent over the insecure channel. Diffie-Hellman is a way of generating a shared secret between two people in such a way that the secret can't be seen by observing the communication. That's an important distinction. You're not sharing information during the key exchange, you're creating a key together. This is particularly useful because you can use this technique to create an encryption key with someone and then start encrypting your traffic with that key. And even if the traffic is recorded and later analyzed, there's absolutely no way to figure out what the key was, even though the exchanges that created it may have been visible. This is where perfect forward secrecy comes from. Nobody analyzing the traffic at a later date can break in because the key was never saved, never transmitted, and never made visible anywhere. The way it works is reasonably simple. A lot of the math is the same as you see in public key crypto in that a trapdoor function is used. And while the discrete logarithm problem is traditionally used, the x to the y mod p business, the general process can be modified to use elliptic curve cryptography as well. But even though it uses the same underlying principles as public key cryptography, this is not asymmetric cryptography because nothing is ever encrypted or decrypted during the exchange. It is, however, an essential building block and was in fact the base upon which asymmetric crypto was later built. The basic idea works like this. I come up with two prime numbers, G and P, and tell you what they are. You then pick a secret number, A, but you don't tell anyone. Instead, you compute G to the A modulo P and send that result back to me. We'll call that capital A since it came from small a. I do the same thing, but we'll call my secret number small b and the computed number capital B. So I compute G to the small b modulo P and send you the result called capital B. Now you take the number I sent you and do the exact same operation with it. So that's capital B to the small a modulo P. Finally, I do the same operation with the result you sent me. So that's capital A to the small b modulo p. The magic here is that the number that I get in step 5 is the same number you got at step 4. Now, it's not really magic, it's just math, and it comes down to a fancy property of modulo exponents. Specifically, g to the a modulo p all raised to b modulo p equals g to the ab modulo p. And g to the b modulo p all raised to the a modulo p equals g to the ba modulo p. Which, if you examine closer, means that you'll get the same answer no matter which order you do the exponentiation in. So I do it in one order and you do it in another. I never know what secret number you used to get the same result, and you never know what number I used, but we still arrive at the same result. That result, that number we both stumbled upon in step 4 and 5, is our shared secret key. We can use that as our password for a yes or blowfish, or any other algorithm that uses shared secrets, and we can be certain that nobody else, nobody but us, knows the key that we created together. So now we've worked with Diffie-Hellman in terms of mixing colors, and we've presented the basic idea of the formula. Let's take a look at a real-world example. Instead of choosing a starting common color, Alice chooses two numbers represented by the variables p and g. P must be a prime number. Let's say that Alice sends a message to Bob, then telling him to use 13 for P and 7 for G. Next, Alice chooses a secret number. Let's say that she chooses 5. We'll call that lowercase a. She then computes the value of uppercase a using the formula uppercase a equals G to the lowercase a power modulo P. That's 7 to the 5th power modulo 13, which gives us a value of 11 for A. Alice then sends the value of capital A, which is 11, to Bob. Bob then selects his own secret number. We'll call that lowercase b. And let's say he chooses the number 8. Bob then performs a similar calculation to determine uppercase b, using the formula uppercase b equals G to the lowercase b power modulo P. This gives us a value of 3 for Bob. Bob then sends the value of capital B, which is 3, to Alice. Alice then computes the shared secret S using the formula S equals uppercase B to the lowercase a power modulo P. This works out to 3 to the 5th power modulo 13, which is 9. Bob can then compute the same shared secret key using a different formula. S equals uppercase A to the lowercase b modulo P. That works to 11 to the 8th power modulo 13, which is 9. And now Alice and Bob both have the same shared secret value of 9, which they can use as a symmetric encryption key. If a malicious person watched the entire communication between Alice and Bob, he wouldn't have enough information to reconstruct that key.